Okay, so now we're ready to take a look at decimal point numbers. So what we saw in the last video is we could store whole numbers using the byte, the short, the int, and the long data type. And we saw that we could represent numbers all the way up to 9 quintillion. Okay, so I just realized, I think as I was talking, my brain wasn't quite working right. I think I skipped trillion. So I just looked up a number system real quick so we could get you the right numbers on these. I totally think I skipped trillion. So anyway, these numbers right here, right? This is hundreds of thousands. Oh, let me bring that back up. Okay, hundreds of thousands, millions, billions, trillions, quadrillions, quintillions. Okay, so you can see 9 quintillion, negative 9 quintillion, the positive 9 quintillion. Right, you've probably never used that word other than just times like this where you're trying to figure out what the next, name of the number of zeros is. So I mean, that's how big longs are, right? It's going to be extremely rare, if really ever, that you'll need numbers quite that big into the quintillion. So long is a pretty good number type. What's interesting is we can actually store even larger numbers in these decimal point number systems. Okay, so that's basically going to be the next thing that we look at, is decimal point number systems. Okay, so decimal point number systems, if you want to store extremely large numbers, they're good to use. Or obviously, if I want to store anything that has a decimal point, like 3.14, we can't actually store that number using one of these whole number systems that I was just using. Earlier, before, I gave the example of maybe if you were selling items on a website, right, and you wouldn't want to use the byte data type because you might have something that was $200 and it would be outside the range of the short. Well, you also wouldn't want to use the byte data type or the short or the int or the long because maybe your price was $59.99, right? That kind of falls within this range, but you just can't represent that 99 cents with a whole number. Okay, so let's go down and look at our last two numbers, which are the float and the double. Okay, so I'm going to start off by, just like I did before, I am going to copy the from the long data type. Okay, I'll go ahead and copy the text, and then I'm going to do the same thing for the print statement, just like that. Okay, so let's go ahead and take a look at the long data. So let's go ahead and update these terms from long to float. Okay, and then here, right, we're going to have now the float data type, and that's going to be float with a capital F, float.minValue. And we'll change long to float, primitive data type, and then float. Perfect. Okay, now you can see I'm having a naming conflict here. So I'm going to go ahead, and I need to do something a little interesting because I have all this other code up here. Let's go ahead and just comment it out for now. Okay, so I'm going to go ahead up in my primitive data types, and I'm just going to literally highlight all of my code under that primitive whole number data types, and I'm going to comment it out. Okay, that way it's just kind of gone for now. Okay, so just to kind of get this code working, I'm going to go ahead and redefine these variables. So I'll add the ints right there, add int back in there just to get it working. Okay, now floats are actually 32 bits. Okay, so a float takes up 32 bits of data, and you'll see number of bytes, num bytes divided by 8. So let's go ahead and change here, float data type, and then float. Okay, now a float data type uses uses this many bytes, this many bits to represent negative numbers from, and we're going to put the lmin and the lmax in there. Okay, now I'm going to go ahead and comment out this second line, and I'll explain why in a second. But let's go ahead and just see what we get. Okay, so the float data type uses 4 bytes, which is 32 bits, to represent negative numbers from, and you see we have an exception, an error. Okay, it says illegal format conversion exception. Okay, so where is this happening? Well, typically what we want to do is we want to look, it'll give you a ton of stuff that you don't recognize, a bunch of different file names you don't recognize, but eventually you should recognize one of these file names, which for us is Les1 primitives. So you want to go and see the first thing that you can find that has your file name, and then it'll tell you what line of code. You can also click 114 right there. Okay, so you can see, well, there's an error somewhere on this line of code. Okay, so let me go back to my console to see where. Okay, you can see it says D does not equal java.lang.float. Okay, and what it's basically complaining about is, if you recall from our formatter, I'll go ahead and open it again. So if I hover over printf, and then I do the format string syntax, S was the generic formatter, right? If I said D, that was allowing me to format integers. Okay, however, this is the first, second, third parameter, right? And over here, the first, second, third parameter is actually a float, right? Lmin is a float. So I'm trying to format a number that has decimal points as an integer. Okay, and that just doesn't work. Okay, instead, we need to format it as a decimal number with decimal points. So we need to use this F. You can see the floating point data type instead to format it. Okay, so we'll go ahead, and I'm just going to change the D to an F in both of these places. Okay, I'm going to leave that comma there because this is going to be a very large number. So let's go ahead and play this now. Okay, so what we see now is I can represent negative numbers from, well, you can see 0 to -1, so that's a little odd. And then non-negative numbers from 0 to, wow, super huge number, right? 300, 340, and so on and so on. A very large number. So what you see here is that our lmin is actually, our float.min value actually just works a little bit differently than the integers. If you recall from the whole numbers, they would always give us a negative number, whereas here we're actually getting just 0. Okay, so I don't really know why. I mean, I guess we can hover over and kind of read, right, at constant holding the smallest positive non-zero float of type float. So for some reason, the min value for the float gives you the smallest positive non-value. If we would go back to, I'll just type it out here, right? We did something like integer dot min value. You'll see that here, let me do a semicolon here. You can see when we hover over here, it gives us the minimum value of integer can have, which is a negative value. So it just behaves a little bit differently with these decimal points. So what I'm actually going to do is I'm actually just going to say max value, and I'm going to put a negative in front of it. Okay, so this is going to be more or less correct. It will be off by like maybe one little bit, but you can see here now I can represent negative numbers from whatever this is, right? This is even bigger than the longs that we just looked at. And then in non-negative numbers from 0 to some huge number, right? Now this is a little bit deceptive because this says to -1, but that's not quite true, right? Because I can actually represent negative 0.01 or negative 0.0001 or negative 0.000001. So really what we should do here is maybe change this to a 0 and then change the type, right, to the non-inclusive in bracket. So if we run this again, we'll see this huge negative number to 0 non-inclusive. So anything just below 0. Okay, and then on the other side, right, we can represent 0, so we'll say inclusive 0 all the way up to this huge value right here. Okay, now this huge value is really ugly to print. Okay, and we're going to get rid of these exceptions in a second. This is from code a little bit further down that we haven't looked at. But these huge numbers are incredibly ugly to look at, right? I don't want to ever see this. I can't comprehend this as a human. I'd have to literally count all these zeros and then, go look up that number system online to see what this number, how to even pronounce it, right? So a better way to represent this number would actually be using scientific notation, and that's exactly what we'll do, right? So we'll go ahead and we'll actually remove, I'm going to remove the comma and I'll just say E instead. Okay, so where we had %F, I can just put an E instead, %E. And then when I run this, you'll see now we get something a little bit nicer, right? Negative 3.402823 times 10 to the 38. Okay, and then very similar up here. So I should hopefully be able to do something like this. I've actually never tried this, but let's try %2. And we do see, right? So we get this now 3.40. So I'm going to go ahead and do that in both places. 0.2. So that way it's just a little bit more readable, right? So 3.40 times 10 to the 38 negative, right? And then 9 negative numbers from 0 to 3.40 times 10 to the 38. Okay. So I'm just going to simplify this again, since we don't get that clear cut like we did in the long from some negative number to -1 and then 0 and so on and so forth. I'm just going to simplify this a little bit to say represent negative and positive numbers from, and then we'll just simplify this so it says that negative, that first value to, we'll remove all the stuff in the middle. So just like that. Okay, so represent negative and positive numbers from negative 3.4 times 10 to the 38 to positive 3.4 times 10 to the 38. Okay. Now, again, here, this wouldn't make sense. Thus, a float can represent 2 to the 32 distinct values, because that's not true. It can represent a huge number of distinct values because of that decimal point. So this sentence only made sense when we were talking about whole numbers. So I'll go ahead and delete that. And then I'm going to come down here. Please enter a whole number within the range. And again, I'm going to change this to very similar, 0.2f, or 0.2e. I'll do the same here, 0.2e. Okay, so let's go ahead and play this, and hopefully that gets rid of that error. All right, so we can enter in pretty much anything now, and it's going to be just, well, okay, because I typed in too many numbers. I always get a little bit ambitious. Okay, let's see, probably have a little, well, okay. My problem is that I didn't finish the code yet. Okay, so I need to also change this to a float. Okay, so float f equals, and I'm going to read in the user's input as a float. Okay, and then down here, instead of L, I'm going to have F. Okay, let's go ahead and change our variables up here. Right, so Alt-Shift-R, we're going to change this from Lmin to Fmin. Same thing here, Alt-Shift-R, change Lmax to Fmax. Okay, and then everywhere where we were printing out values, let's do the same thing here, right? So let's do .2e, %.2e. Okay, I'm going to do the same thing on the last one, %.2e. And on the middle one, I'm actually going to do it as an f. Okay, I'll do something like this, 0.4f, for instance. Okay, because I'm probably not going to type in a huge number, although maybe I could. I'll go ahead and do that. I'll say, well, let's just leave it like that for now. We'll show you what happens. Okay, so let's type in some number. Okay, so you can see it's printing it out with 4 decimal points. I could come in here and add a comma as well before the 0.4f. If I want to make that a little bit more readable. Okay. I could also represent numbers with decimal points, right? So 3.14. Okay, or a negative number, negative 5.4 something, right? So it's just when it's printing it, it's going to chop off this precision. You can see all these extra numbers past the 4 decimal points. You can see it even rounds it, right? It was 0.24189. It rounds up that 89 to 9. Or obviously I can have just a huge number in here. Now, I hit enter a little too early. Let's do this one more time. So you can see I can represent absolutely huge numbers. If I do want to, I can change this F to an E, and that will now give me scientific notation there. Okay. I don't know if the comma works. Yeah. Okay, so anyway, you can kind of leave that however you want. I'm actually going to leave it as 0.4f, just because that's typically how I'm going to enter in numbers. I'm not going to go crazy with them, right? Let me put the comma back in there. Perfect. Okay, so the last thing to do is take a look at the double data type. Okay, so let's go ahead and I'll copy the basic print info. And I will copy the user prompting for the user. And we'll just change these really quickly. Okay, so again, I'm going to go ahead and comment this code out. And I'm going to change float to double. Okay, I'm going to Alt-Shift-R fmin to dmin. And I'm going to Alt-Shift-R fmax to dmax. I'm going to change this float wrapper class to the double wrapper class. Both of those places. And a double is called a double because it is twice as big as a float. So it's 64 bits. On the print statement, I'm going to change float to double. Okay, and then please enter a whole number within that range. And of course, double D equals scan.next double. Go ahead and delete that. And then last but not least, just change this F to a D. Oops. Okay. So let's go ahead and give this a try. Now I'm going to go ahead up here. I'm going to uncomment my float code. So highlight that and then uncomment it. And then go ahead and save it. And now notice, obviously, I'm going to have this redefinition of these num bits and num bytes. So go ahead and delete the int on both of those. Okay. So let's go ahead and give this a play. And what we'll see is now my float. Type in some stuff. And what you'll see down here, right, is my floats. Sorry, I'm going to change one more thing here. On this initial print statement, let's change that to double. And I'll play it one more time. Give it some numbers. Give it some numbers. Huge numbers now. Now I really can't go outside of that range, right? So what you'll see is the float, right, can represent numbers up to 3.4 times 10 to the 38. The double can represent numbers up to 1.8 times 10 to the 308th, right? So this absolutely huge number. I can't imagine a use case where you're going to need to represent numbers up to 1 times 10 to the 308, right? So you literally, you know, on this double, you could just go crazy on numbers till you get tired of typing, and you're not going to overflow that. Okay. So that is the two different decimal data types. As you can imagine, you're never going to need something bigger than a double, at least not for a very long time, you know, until something fundamentally changes with the types of problems that we're trying to solve with computers. Okay, so that would be the float and the double data type, which allows you to represent numbers using decimal points. Of course, we didn't demonstrate it, but I can also represent numbers like this. Now, I'm not displaying it up into 4 points, but if I wanted to, right, I could do that. Change it to 40 decimal points. So I just wanted to show you that I'm not going to lose that data per se, right? You can actually see it's storing at 54165, 54165. It does seem to chop it off at a certain point, but it can store a pretty good amount of precision in terms of the decimal points. Okay. All right, so those are the decimal point number data types, the float and the double. Double is absolutely huge and float's pretty huge as well. Okay, so in the next video, we're going to tackle our last two primitive data types, which are the boolean and the char.